Hello, I am Pradeep Kumar, Professor. Welcome you to the lecture on fluid properties being presented in four parts as listed. In this lecture, that is third part, we will discuss various aspects of surface tension, development of capillarity, followed by ascertaining ourselves with multiple choice questions and solving the problems and then concluding with summary. This presentation encompasses concepts needed for various competitive examinations like UPSC, GATE, Public Service Commission examinations of various states, etc. The presentation also includes discussion on the questions that may be anticipated in the interview. Now, let us proceed with the agenda of presentation. Let us recollect our school days. Raindrops thrilled us and fascinated us. Some insects challenged us to hop on water surface, which they could easily do. Not a mercury is so quick to regain its shape whenever we have disturbed it. Gently placed pin whispered something about the surface in spite of our best efforts to unite water drops and lotus leaf we could never win. Drop of blood raised our eyebrows, but all of them unquestionably wanted to tell us something. Can you guess? Yes, two things. Liquid droplets are spherical and surface supports small weights. As human beings, we were inquisitive to find out why drops attain only spherical shape, not the cubical or cylindrical. Also, we were wondering who gave the surface the Horlicks or Bonvita to get energy to perform the work of supporting the weights. Now, let us explore this teasing game by the Mother Nature with a small visualization. Consider a beaker having a liquid, say water, in it. Also, as shown in figure, consider water molecules at A and B. While the molecule at A is at some depth from the surface, molecule at B is on the surface. Let the surface be in contact with some other fluid, say air. Now, once we have given a special preference to molecule at A, the surrounding molecules feel jealous and start pulling A. Unfortunately, the pulling is same in all directions as A is surrounded by water molecules on all the sides. All the forces balance each other. But the molecule at B is pulled by water molecules from the bottom and air molecules at the top. So, molecules on the surface experience a net downward pull, because of which surface molecules try to penetrate into the liquid. But this inward movement of surface molecules is resisted by the molecules inside the liquid, especially by the molecules just below the surface. So, there will be a fight between the surface molecules and their neighbors. Now, just below surface molecules will be subjected to compression, which causes the liquid to minimize its surface area and hence is the spherical shape. Further, the compression effect on the just below surface molecules makes the surface molecules move close to each other, of course, not into the liquid but on the surface only. So, the surface molecules move parallel to the surface, close to each other, but still experiencing the unbalanced residual downward pull. The hidden energy arising due to unbalanced force makes the surface act as a stretched membrane, and this is the reason why the surface which is under tension gets the energy to support the external weights. The property by which molecules laying on surface of a liquid make the surface spherical and also possess energy to perform a work is known as surface tension. As the surface tension depends upon the length of contact between the molecules, it is the linear force as shown in figure. Further, it is denoted by the Greek letter sigma, and has the dimensions of f power 1, l power minus 1 or m power 1, l power 0, t power minus 2. It has the units in SI and MKS absolute system newtons per meter, and in MKS gravitational system it is kilogram force per meter. Further, a pressure difference is established across the surface wherein the effect of surface tension is felt. For example, liquid drops, bubbles as well as jets. Now, let us quantify the effect of surface tension in terms of additional pressure. As shown in figure, a droplet is a solid body, that is, it is not hollow inside like a bubble. Therefore, only outer surface will be in contact with the other type of fluid. Let us consider the droplet be a water droplet and outer fluid be air. So, only outer surface of the water droplet will be in touch with the air. As we know, surface tension is a linear force. The maximum length of contact between the droplet and the air is circumference itself. So, it comes to S is equal to sigma into 2 pi r. Force due to this additional pressure is equal to P into pi r square. Why pi r square? It is the projected area on which pressure force is acting. That is, projected area is the characteristic area normal to the pressure force. That's why we take the area as pi r square. At equilibrium, surface tension force must be equal to pressure force due to additional pressure. Equating equations 1 and 2, we get P is equal to 2 sigma by R, where R is the radius of the droplet, sigma is the surface tension of the fluid, and P is the additional pressure. Now, additional pressure inside a bubble due to surface tension effect. As shown in figure, a bubble is hollow inside. It will have two surfaces in contact with different types of fluids. The surface tension force is 2 times here when compared to the first case, whereas pressure force is same because projected area is same. Now, equating equations 3 and 4, we get the additional pressure is P is equal to 4 sigma by R. Additional pressure inside a jet due to surface tension. Just like a droplet, jet is also a solid. So, as shown in figure, only outer surface of the jet, that is one surface, will be in touch with the other type of fluid. So, let the length of the jet be L, radius be R. Now, the length of the jet which is in contact with the other type of fluid is 2 times the L. Therefore, surface tension force becomes sigma into 2L as shown in equation 5. Force due to additional pressure is P into 2RL, where P is the additional pressure, R is the radius of the jet. It may be noted that the projected area of the cylinder on which pressure force is acting is similar to that of a rectangle of size 2R by L. Therefore, equating equation 5 and 6, we get P is equal to sigma by R with usual notations. Before proceeding to the next topic, that is capillarity, let us revise whatever we have discussed in the form of questions. Surface tension decreases with increase in temperature. Why? Increase in temperature means decrease in cohesion. Decrease in cohesion means decrease in surface tension. What is the effect of presence of surfactant on the surface tension of water? As you can see from the figure, the presence of surfactant reduces the cohesion among the water molecules because this is a foreign body. This reduces surface tension. That's why water moves deep into the openings of the fibers for more effective washing. Another important point which we have to bear in mind is whenever surface tension value is mentioned, it is mandatory that we should mention between which fluids we are referring to surface tension and also the temperature at which the surface tension is measured. The following table presents the values of surface tension of normally used fluids. Now let us start another subtopic, capillarity. I am sure when you were young, you must have been fascinated by the flame at the tip of a wick. Oil is somewhere and the tip of the wick is somewhere else. Leaves of the plant are very fresh and greeny, but water is supplied at the root. Rays of water in the soil pores, as you see on your right hand side. Rays of water in a thin glass tube. Fall of mercury in the glass tube. Now, the question is, who is carrying the fluid, that is oil or water, to the place of use? There were no Ola or Uber here. Then, what is the reason? Yes, again, it is a game by molecules. The love and hate, that is cohesion and adhesion between the molecules, is the main reason for this. Now, let us peep into the action by these forces. Immerse a thin glass tube in a liquid. Depending upon the type of liquid, of course, glass is same, two situations may arise. That is, adhesion between glass and liquid is more than cohesion between liquid-liquid molecules. And the second one being cohesion between liquid molecules is more than adhesion between glass and liquid molecules. In the first case, some liquid molecules diverge to their friends and move away with their new friend, that is glass molecules. Liquid molecules will creep along the glass surface and also form a concave upward surface as shown in figure and form an angle of contact of tangent with the glass surface, that is alpha less than 90 degrees as shown in figure. Examples being rays of oil, water, sap, etc. In the second case, the force of attraction between liquid molecules is more than that of liquid and gas molecules. Liquid molecules will be repelled from the glass surface of contact, because of which liquid surface becomes convex towards the center. That is, meniscus is convex upwards as shown in figure, and the tangent to the meniscus makes an angle greater than 90 degrees with the glass surface. And finally, the property of rise or fall of a liquid level with respect to surrounding liquid is called capillarity. If the liquid rises is called capillary rise, otherwise it is called capillary depression. Now, let us quantify the capillary rise or fall. Before that, let me ask you an interview oriented question. What is the practical application of this aspect? That is, why should we quantify the capillary rise or fall? As shown in figure, rise of groundwater due to capillarity may make even highly fertile soil into barren, that is alkaline or saline soil due to waterlogging in the root zone. And as shown in the second figure, whenever capillary rise is more than freeboard, which is similar to parapet wall of the house, then due to capillary siphoning, the reservoir loses its capacity. Therefore, estimation of capillarity is a safe measure to ensure functional efficiency of a project. Therefore, let us estimate the magnitude of the capillary rise or fall. The magnitude of capillary rise or fall of a liquid depends upon the balance between the weight of the liquid inside the glass tube as shown in the figure and the component of the surface tension in vertically upward direction, that is W and S respectively. Now let us take the first part, that is weight of the fluid inside the glass tube. Weight can be written as weight by volume into volume of the fluid. Then weight by volume is specific weight of the fluid, but specific weight of the fluid is equal to specific gravity of the fluid into specific weight of water. Therefore, in terms of symbols, it comes to G into gamma W, where G is the specific gravity of the fluid, gamma W is a unit weight of or specific weight of water. The second part is volume of the fluid inside the glass tube. It is given by pi r square into delta H, where pi r square is the cross-sectional area of the glass tube and delta H is the capillary rise or fall. Then it comes to W is equal to G gamma W into pi r square delta H. Surface tension along the tangent of the meniscus as represented in the figure as S1 sigma into periphery of the contact, because sigma is a linear force. Here length of contact is the circumference of the glass tube 2 pi r. Therefore S1 is sigma into 2 pi r. But what we want is vertical component to balance the weight of the fluid inside the glass tube. Then the vertical component of S1 becomes S is equal to S1 cos alpha, that is sigma into 2 pi r cos alpha. On equating equations 3 and 5, we get delta H is equal to 2 sigma cos alpha by G gamma W r. Another important point on the field for simplifying the problems, we assume meniscus as hemispherical and the glass tube, that is inside the glass tube, is clean. Therefore alpha is 0 for the case of water and alpha is equal to 180 for mercury. So using equation 7, we can calculate either capillary rise or capillary fall. Now a few multiple choice questions and filling the blanks. Rise of a liquid in a capillary tube decreases with increase in diameter, increases with increase in diameter, decreases with increase in surface tension, increases with compressibility. It is obvious from the equation the capillary rise is inversely proportional to the radius. The answer is A. Falling drops of rain acquire spherical shape on account of viscosity, surface tension, vapor pressure and compressibility. The answer is B. Surface tension has the dimensions of F, Fl power minus 1, Fl power minus 2, Fl power minus 3. The answer is B. Capillarity is due to adhesion, cohesion, both adhesion and cohesion, neither adhesion nor cohesion. The answer is C. Capillary rise is higher in lighter liquids. Say yes or no. We can see capillary rise and specific weight are inversely proportional. So the answer is yes. Angle of contact alpha and capillary rise are inversely related. Yes or no? It is obvious from the above equation that capillary rise and cos alpha are directly proportional to each other. But cos alpha value decreases with increase in the value of alpha. So the answer is yes. Next, for water, meniscus is concave downwards. Yes or no? No. Capillary rise is higher in sandy soil compared to that of clayey soil. Yes or no? The answer is no, because the size of the pore in a sandy soil is more when compared to that of a clayey soil. Now let us work out a few problems. Determine the pressure inside a drop of diameter 0.06 millimeters. Pressure outside the droplet is atmospheric, that is 1.0 kilogram force per square centimeter at 20 degrees centigrade. Surface tension of water with air at this temperature is 0.0073 kilogram force per meter. The problem is on fluid properties and units are not given in a single system. Coming out to the data given, size of the drop as 0.06 millimeters, outside pressure is 1 kilogram force per square centimeter, temperature is 20 degrees centigrade, the sigma, that is surface tension, is 0.0073 kilogram force per meter. Coming out to the assumptions, continuum approach is valid and no experimental errors. It is a problem pertaining to the determination of pressure inside the drop. So, The surface tension will be acting only on outer side of the drop surface. Using the corresponding equation, that is P is equal to 2 sigma by R, substituting the values of sigma and R in the above equation, we get the additional pressure, that is P is equal to 0.049 kilogram force per square centimeter. At this stage, we have to be very careful. He is asking you to determine the pressure, but the above equation gives you only additional pressure inside the droplet. Therefore, the total pressure is equal to outside pressure plus additional pressure. It comes to 1.049 kilogram force per square centimeter. Determine the capillary rise or fall when a glass tube of 3 mm diameter is immersed in water and mercury. Sigma of water with air at 20 degrees centigrade is 0.0074 kilogram force per meter. Sigma of mercury with air at 20 degrees centigrade is 0.05 kilogram force per meter. The problem is on fluid properties. Units are not in a single system. Data given: diameter of the tube as 3 millimeters, surface tension of water with air at 20 degrees centigrade is 0.0074 kilogram force per meter. Surface tension of mercury with air at 20 degrees centigrade is 0.05 kilogram force per meter. Coming out to the assumptions, continuum approach is valid, no experimental error, and glass tube is clean. Specific gravity of water is 1, specific weight of water is 1000 kilogram force per cubic meter, specific gravity of mercury is 13.6, specific weight of mercury is 13,600 kilogram force per cubic meter. We have to determine a rise of water and fall of mercury using the equation delta H is equal to 2 sigma cos alpha by G gamma WR. Now let us take first case, capillary rise of water. As shown in figure, since we assumed the glass tube to be clean, alpha is 0, so cos 0 is 1. Substituting these values in the above equation, we get capillary rise of water as 9.9 millimeters. Now, case 2. Assuming alpha as 180 degrees, then cos 180 is minus 1. Then substituting these values in the above equation, we get capillary fall of mercury as 4.9 millimeters. The negative sign takes care of capillary depression as shown in figure. So, before winding up, let us sum up whatever we have discussed in this presentation. We had a discussion on various aspects of surface tension, expressions for additional pressure due to surface tension in different case studies, the process involved in the development of capillarity and quantification of capillary effect, and finally applications of surface tension and capillarity. We also discussed a few multiple choice questions and strengthened ourselves by working out some problems. In between, we discussed various interview oriented questions. Before signing off, I request you to leave your comments in the comment section to enhance communication between us. Like and share the video among your friends and concerned. Subscribe to my channel by clicking the bell icon, the best way of getting updated with the information on the latest videos pertaining to the other topics of fluid mechanics, hydraulics and hydrology in addition to career planning. Thank you very much and wish you an excellent future.